What's up, guys? Another video on structure and bonding. This is the second video on simple molecules. It's the second one of three, actually. And this one, they all really do tie together. Before we carry on, though, like, subscribe, share. Let's grow this channel. Let's crack on. So, first of all, when we're thinking about bond polarity, the first thing we need to think about is electronegativity. So when we talk about electronegativity, that is the ability of an atom to attract electrons within a covalent bonds. So if we take this as an example, if this is our molecule, and we said that this is the more electronegative of the two, the electrons won't be here, they will draw slightly closer. Okay, and what that will do is that will affect the charges of these. Now, this will be ever so slightly negative, so we call this delta negative. This D means very slightly, and this will be delta positive. We'll explore that a bit more in a bit. So, looking at the periodic table, I've only got the top three rows here, but essentially, we can attribute these values. I think this is called the Pauline scale. I can't remember. But anyway, we can see these values as we move across the periods go up. We can see as we go down a period, the values go down. Okay. Now, what we have is this general pattern where if we move from the bottom left and move up towards the top right, we have increasing electronegativity. And obviously we've got no numbers attributed to group 0. I hope you can understand why that's very much to do with the fact that noble gases are very rarely involved in covalent bonds. So why have we got these values? So fluorine, the most electronegative. What we find as we move across a period, a couple of things are happening. The atomic radius is getting ever so slightly smaller and smaller and smaller. What's also happening is the number of protons inside the nucleus is increasing one by one. And as well, the electron shielding is staying the same. So what do I mean by that? So we've got this sort of structure. If this is lithium, we've got 1 electron in the outer shell, 3 protons. Beryllium, 2 electrons in the outer shell, 4 protons. So here, the number of electrons that are in the way of the nucleus is not changing. And that will carry on and carry on and carry on until we start adding a new shell. And as we add a new shell, that's why all of a sudden this number drops again. Because now the atomic radius and the electron shielding has increased. We can look further at a couple of examples here. So let's say this red substance, this red element, could be one of 3 things: oxygen, fluorine and chlorine. This is a simplification, of course. So if we take oxygen, which has a number of 3.5 in terms of electronegativity, we can see that fluorine is then 4.0. So a few things have happened there. Electron shielding will remain the same, but our number of protons has increased. As well, the atomic radius will slightly have decreased. So that's what's changed here. Now if we move along to chlorine, which then drops to 3.0, you can see we've got many more protons, but the atomic radius is much bigger because we've got this extra shell of electrons. And also the electron shielding will therefore be greater as well. So again, it often happens in chemistry that we're talking about these 3 things: atomic radius, nuclear charge and electron shielding. So for more electronegativity, we need the atomic radius to be as small as possible. We need the nuclear charge to be high, and we need the electron shielding to be low. So we've got these factors. We need to think about the position on the periodic table when it comes to this. We'll talk about periodicity and things like that in a later topic. So in terms of how this links with this other stuff, so electronegativity can cause polar bonds, as we see here. This is polar in that we have a delta negative end and a delta positive end. But sometimes it's not going to create a polar molecule, and we'll see what that means in a sec. It's going to help us to draw these out. So carbon dioxide, these double bonds act very similar here. So we've got 180 degrees, and this is linear. Does it have polar bonds? Yeah, clearly this oxygen is going to be more electronegative than carbon. So we can say delta negative, therefore carbon, delta positive. So absolutely we've got polar bonds. Is it a polar molecule though? Well, we've got lines of symmetry here. So here, if our molecule is symmetrical, we're not going to have any polarity in there. The poles are almost going to cancel each other out. So here, because we've got symmetry, despite the fact we've got polar bonds, it's not a polar molecule because of this symmetry. Water we looked at last time as well. So we've got O, H, H. We say this is bents. Remember, we've got our lone pair, or two lone pairs of electrons here. And we've got a bond angle of 104.5. Again, this time, oxygen more electronegative, hydrogen delta positive, right? So absolutely, we've got polar bonds. Now, is there any symmetry here? Absolutely not. So yes, we have a polar molecule. And this idea about polar and non-polar molecules is going to become very important next video when we start looking at intermolecular forces. So then on to ammonia. Ammonia is going to look something like this. Bond angles of 107. And the shape, we call it pyramidal. Now again, nitrogen is going to be delta negative. It's more electronegative here, delta positive, delta positive. So absolutely, we have polar bonds. Have we got symmetry here? No. So it's a polar molecule again. Then we get on to ammonium, which is a good example of dative covalent bonding. So we've got an H plus ion has bound on to this lone pair of electrons here. And this is tetrahedral, got bond angle of 109.5. And again, nitrogen, delta negative, the hydrogens are delta positive. So absolutely we have polar bonds. Do we have a polar molecule? No, we've got lines of symmetry again. So because of that, absolutely not. And again, a few things can change that. So if, for example, one of these was Cl, for example, now all of a sudden this symmetry is broken. Okay, then we have a polar molecule, but we don't have that. And where this will apply is for linear, for trigonal planar, for tetrahedral, for square planar, and for octahedral. All of these, we can have these lines of symmetry as long as these R groups are sort of basically all the same. In terms of the questions that you get asked, that will always be the case. Look, give that a go. Give that a go for CF4 and XCF4, which is a question I asked about last time. I'll answer that at the end of next video, but this will help with that as well. So this was our question at the end of last video. So CF4, carbon is in group 4, so has 4 electrons in the outer shell, so it will form 4 covalent bonds. All of those are done. So we're going to have this. Bond angle of 109.5, tetrahedral. What's our explanation? We've got 4 bonded pairs, pairs of electrons, repel as far as possible. With XC, again, remember, XC is in period 3, so it can act a little bit funny, right? XC is in group 0, so here it has 8 electrons in the outer shell. 4 of those electrons are going to be shared with fluorine. So here we're going to have 4 bonded pairs again. And 2 lone pairs. So what structure do we have there? We have this. We have our square planar. So we've got XE with RFs. 90 degrees. And here we have the same sort of line. Pairs of electrons repel as far as possible. But then we need that last bit as well. Lone pairs repel further. Great. Look, I hope that's helpful. Next time we'll look at intermolecular forces, so more opportunity to see some of this stuff in context. So see you next time. Until then, happy revising.